So as you know, this session is regarding the nonlinear modeling and simulation using OpenSys. Means I think all of you have already have some exposure to OpenSys, so you'll be knowing already. I am not going to again initiate the discussion on OpenSys. So as we'll go with the discussion in modeling and simulation, wherever it's coming, some important topics we'll discuss there only. So this is regarding the modeling and simulation of structure using the concept available in OpenSys, and for simulation we'll be using the software REOS, that is our in-house developed, and including the result visualization and everything will be done in the software. After that, if you want to run the same model in the traditional way using the command prompt or script based analysis, that also will show whatever script you are generating in the software, that you can run uh, as usual how you are doing using the command prompt based analysis. Okay. So what we'll be doing here is this one. We'll start with a modeling of a 10-story building, and we'll analyze the structure first for the model analysis. Then we'll analyze for the linear time history analysis, and we'll analyze the same structure for pushover. And finally, we'll also perform the nonlinear time history analysis. So the idea is just to show you the entire workflow implemented in the software, not to compare the result of one analysis with the other one. Once you are handy with the software, so after that you can compare the results yourself. So here, if we go in details with the discussion of the result as well as the comparison, it will take a lot of time. So we'll just go through the workflow implemented in the software, whatever you need to use for each of these analysis and the corresponding modeling. Those things we'll discuss, and result discussion we'll just go through them, see how you can visualize the results, but not a detailed discussion on the results itself. Okay. So I think I'm assuming that all of you have some exposure to OpenSys, so you already know how to install, where to download the software, and how to install in your system, all those things. But if suppose any of you are not already aware of how to install the software in your system, then we already conducted another session earlier where we have in details discussed and demonstrated these steps. Okay, so after this session, when I'll be sharing the recording, I'll also share the recording of the previous session, so that if you have any doubt regarding the installation of OpenSys in your system, then you can follow that tutorial and you can do it yourself. All the steps are discussed in detail, so I'm hopeful that you will not have any doubt. But still, if you get doubt after that, just reach out to us. We'll assist you in installation of the software. So this is the structure we are going to discuss today. This is a simple movement frame structure. This is the plan view you can see in X direction. Actually, X is in this direction here in this diagram. So there will be 4 bays in X direction, and there will be 6 bays in Y direction, and the building is symmetric. So this is what we are going to take up today, and these are the steps we'll be following. This is not a traditional steps in the software. It is in any software. Wherever you want to analyze a structure, you first have to model, you have to define the geometries, materials, elements, all these things. So these are the general steps you have to follow. Okay, so now let's go back to the software. So before starting, actually, I already have prepared this model for all the different analyses. So this is how it looks like after the completion of the model. Okay, so the same structure will replicate now, demonstrating all the steps. So when you start the software, it the interface starts with this view. It looks like how you can see now. So first what you have to do is, the first thing, you have to go on this option. Okay, edit. So we'll first start with defining the number of stories, then defining the number of grids in X and Y direction. So this is going to be your first step when you start working with REOS. Okay. So here you can define any number of stories. Let's say I'm defining 10 stories. Okay. And if you have um, uniform story height, you can define here. By default it will consider as 3000 or 3 meter. And before going forward, let me also let you know that the software is unitless. Okay, you can work in any unit you prefer. This is like aligning with how OpenSys works. OpenSys does not give you any particular unit consistent version. Okay, that is completely unitless. So you have to take care of the unit whatever you are going to use. Okay, so in our software also it is same thing, no unit. So you'll define your own unit system in the modeling. Okay, now for this demonstration I'm using Newton second unit system. Okay, so accordingly you have to enter all the distances in and all the forces in Newton. Okay, so now for this demonstration, we are assuming that our story heights are uniform and 3 meter height. So it will be 3000 mm. Okay, and we are defining total 10 stories. So here you can see stories are updated. Similarly, now you'll define the grid system. Now here you can define the grids and spacing for each base along both the direction. Okay, now as we have seen, we have 4 bays in X direction. So you have to actually, this is not grids, actually number of bays. So the syntax errors, we'll update this one. Okay. So here you have to define the number of bays, not number of grids. So 4 number of bays in X and total 6 number of bays in Y. Okay. Then the length of first bay is, means span is 5000 then you have 3000, 3000, and again 5000. So first it is 5000 then 3000, 3000, and 5000. And for Y direction this is, I guess, 5000, then 5000, then this is, I think, 4000. Yes, then again 5000. So our grids and number of stories are defined. This is how it looks like after defining the grids and stories. Okay. Now you have to define the nodes. For that, you start from the base level. So base level means the zero story. Okay. So click on that, then click on the plan view. So it will give you the plan view for the selected story here. Okay. After that, you go to add node, then click on the joints where you want to assign a node. Okay, so this is the workflow currently used in the software, but we have a plan for upgrading this so that you don't have to define the nodes directly. You can define the members. It will be available in future version. For now, this is the concept you have to follow. So actually we have shortcuts, but before using the shortcut, you have to define at least one floor so that you can copy the properties from one floor to the others. Okay. So for defining that first floor, we have to define some nodes. Then you go to the first floor, do the same thing. Okay, so this much we need to assign manually for the nodes. Then you connect them using the line elements. Okay, so we have done with the definition of one floor. Actually, you have not yet assigned any material or element properties. This is just the wireframe model. So now what we'll do is we'll copy this property from first floor to the all other floors. Okay. So for that, you have to again go to edit, then click on this extrude. And now see, we have one floor already defined and another nine floor we have to define. So enter here nine and the copy will be done from the first floor. Okay. Then click OK. Now you can see whatever properties you have assigned in the first floor, the same thing has been copied to all the other floors. Okay, so this is how you can use the shortcut. And now, in a similar way, we'll define the vertical members for one grid line. After that, we'll copy it to all the other grid lines. Okay, so for that, you can open any of the elevation view. Let's say I want to open this one, and again add line and join the nodes. Okay, so now we have completed one bay by adding the vertical elements. Now we'll copy these vertical elements from this bay to all the other grid lines. Okay, so for that again you go to edit, then use this replicate option, and now you have to decide in which direction this copy is going to be. Okay, so here you can see the axis, we have to copy along the y direction. Okay, so you click on this y grid, and here you'll choose from which grid you are going to copy. Now here you can see, let me disable these labels. Okay, and also reduce the line thickness, and also the node size. Okay, so we can see it more clearly. So now you go to replicate, click on y grid, and select the grid from where you are going to copy. So here you can see this is the grid A, so we are copying from A to B. So here it is A selected, and you have to provide the offset along y because we are going to copy along the y direction. Okay, and this span is 5000 mm, and click OK. So here you see it is created along the Y grid. Similarly, now you can again go to the same replicate option, click on Y. Now you have two options, either select A or B, and accordingly you have to enter the distance here. Okay, let's say now I want to go from B. Okay, so again this distance is 5000 mm. So you will give 5000 here, and okay, then again you can now choose C, and the distance is now 4000. The again 4000. Now it is 5000. Okay, so before pressing the OK button, here see you have one more option, orientation angle. Okay, so this is not uh, frequently used, but suppose you want to copy the properties at any radial direction. Okay, so here you can define the angle, let's say 30 degree, 40 degree, like that. So the properties will be again copied in the defined radial direction. So it's sometimes required, although not used frequently, but it is available. If you want, you can use this. Okay, so our wireframe model is now completed. Now the task is to define and assign the properties like materials, elements, all those things. Okay, so before doing that, let me save this model. Um, okay, so we are starting with the elastic model. Then we'll copy the same model and convert it into the inelastic model. Okay, so for that, first you need to define the materials. Now here what we are going to do is we will define the means model the beam members using the frame element, and elastic beam column element is going to be used. Then for column members, for the elastic structure, we have two approach. Either you can use the elastic beam column element, or you can use the fiber section approach and define the means assign the elastic section in the space of fibers. Okay, but now actually we have not yet implemented the fiber section. for the means elastic section for the fiber sections. So currently defining the elastic member for columns using the fiber sections is not possible. Okay, but you can define the fiber section for nonlinear model. We'll do it soon. So if you're thinking of using the uh, fiber section modeling for the elastic model, then it will be available soon. It's not a task like we cannot actually, we just forgot to implement this one. Okay, so it will be done soon. Now what we'll do, we'll model the beam members using elastic beam column as well as the column members for the elastic model. Okay. Then when we are modeling the nonlinear members, then we'll replace the elastic member for columns using the fiber sections. Okay. So first we have to define a elastic material. Actually for elastic model it is not required, but still we'll define everything, and whatever is needed that we'll call later on. Then we need a IMK model for modeling the hinges, plastic hinges for beams. Then we need a concrete model for fiber sections. We also need another concrete model for, like we have to define confined and unconfined concrete. So we need two model. Then we need steel. For steel, we can use either steel, or there is another material, hysteretic, which I prefer for cyclic loading assessment. So you can use whichever you want. So I think we have defined all the materials required. Now this is the elastic material. You can name it as whatever you want. And some high elasticity value you have to, this is like stiffness, elastic stiffness. So here the concept is the stiffness of this material should be at least 100 to 1000 times higher than the stiffness of your actual members where you are simulating the nonlinearity. Okay. So normally for your members, for example, you have a 400 by 400 section. So the stiffness generally varies from 10 to the power 10 to 10 to the power 11 in the unit system I have chosen. So here this elastic material I have defined as a 10 to the power 13. So it is roughly 100 to 1000 times. Then this is the hysteresis model for plastic hinges to be assigned to the beam members. Although this is going to be elastic model for this part, but later on we'll need this one. So we are just defining everything we need. Okay. So this you can say uh, beam hysteresis. And now here this parameter comes from the calibration. Okay. Normally, if you are familiar with like ETAPS, these values comes from the ASC 41 curves. Okay, there is a code ASC 41 for nonlinear analysis. Okay, so this modeling parameters, backbone curve modeling parameters, is governed by the ASC 41. But here we have not yet implemented ASC 41, so you have to calibrate these values yourself and assign. Okay. Now, since we do not have calibrated values, based on my experience with my research, I am defining some values. Here it is 1.5 into 10 to the power 10 stiffness. Okay. So this is for a member section of 250 by 450 mm and using a steel in the range of 2 to 2.5% of the cross section. Okay. So this is not actual values, but roughly for this demonstration purpose we are using. And this is the uh, plastic rotation before peak. Then this is the plastic rotation after peak. So, and this is the ultimate rotation. This ultimate rotation actually has very little role, so you can define very high values also. It doesn't matter actually. So I'll show you the actual backbone curve of this model. After that, you'll understand these three values. Okay, and this is the yield movement. Here it is. Let's say I'm taking from another example I have used in my research. So this is not actual values. 93 kilonewton meter, and this is the ratio of ultimate moment to the yield moment. We are taking 1.1. Then this is the ratio of residual capacity to the yield capacity. So we are not assuming any residual capacity, so you can keep it as 0. Okay. Now whatever you have defined for this direction, the same thing you have to define for the other direction. Okay. So either you can define same things, or you if you have different properties, then you can define it as different. Okay. This is 0. So up to here, this is regarding the definition of backbone curve. Okay. So if you are using ASC 41, you can calculate these values from the ASC 41 and define here. Okay. All these values. Now from here on, from lambda s, these are the cyclic degradation parameters not available in ASC 41. This is specific to this material. These things you have to calibrate. There is no other choice. Okay. So we have a model calibrated for this purpose. Although I'm not going to display here this model, but we have developed that one. If you are willing to use that model, you can just reach out to us. We'll share that model, or there are literature available. You can follow that also. All these things are available with us. You can just let us know if you need. We'll share the documents. Okay. Now, so I'm just referring from my study these values, and this four you can keep by default, and this also by default one, and this is the pinching parameter. You can I have this as zero point 0.7 and this as 0. Okay. So this is defined. Then you can define the concrete unconfined. I am assuming 30 MPa, the compressive strength of concrete. Then ultimate strength, very little role, so you can give some realistic values. And this, let's say, the ultimate strain is 0.004. Then this is the stiffness degradation you can keep by default, and tensile strength I'm ignoring for concrete. Similarly, you can define the confined concrete. Okay, for defining the confined concrete, I need to first define this section because it will use the geometric properties from the section. So let us define a section first. So we are defining a fiber section here, and okay, this we'll write later on. First, we have to define the material. This is core. So we are defining this as the confined concrete. This is unconfined, and let's say we are using the histolytic material, and we are using 3 by 3 fibers in each direction in the core. And here now you can, okay, we have to actually give this one. So for columns, we are using 450 by 450 section. Okay. Now you can define the reinforcement layout. Okay. So it is asking you whether you have a symmetric reinforcement layout or not. So accordingly, you can check this box. Okay. We have a symmetric layout, and here you define which face, either all face or opposite face. Okay. We are assuming the symmetric reinforcement layouting for all the faces, and here you define the corner rebar diameter, let's say 20 mm, and we have four rebars on each side. Okay, so you have two rebars between the corners. Okay, and internal rebar diameters, let's say 20. Let us give this as 25. Okay, then generate layout, and okay, so this is your fiber section. Now you can open this once again to confirm. Here you see. Okay, so now you can go to assigning the confined concrete model, not assigning, sorry, defining the confined concrete model, concrete confined. Could you please mute your mic? So this is concrete confined, and here you select the confinement model and the geometry of your cross section. Okay, so this is the unconfined properties you are defining, and see the geometric properties it has taken from the section where you have assigned this material. Okay, so cover we are assuming 40 mm, and this longitudinal rebar diameter we have used two different diameters, 25 and 20. So here you have to define any one. Longitudinal rebar has very little role in confinement model. So just give some average values. Okay. So let's say 20 because we have higher number of bars using 20 mm die. Okay. So we are assuming the spacing between the transverse reinforcement is 100 mm and diameter of the transverse reinforcement is 10 mm, and the steel grade of transverse reinforcement, let's say 500 MPa. Okay. So number of legs, two along both the directions. Then you can click on this option, and you can click on this option, and accordingly the properties for the confined model will be updated here. Okay, again here we are ignoring the tension strength of concrete, then press OK. Then for reinforcement we have two options. Now I am going to use this one. Okay, so this is rebar hysteretic. This is the yield strength, let's say 500 MPa, and this is the yield strain, roughly this one. Again, you have to see what is the actual stress strain curve for your steel. Accordingly, you will define these parameters. So this is the ultimate strength, not ultimate. This is peak strength, and this is the strain corresponding to peak strength. This is uh, mostly zero point 0.01 to 0.02 in between that. Again, you'll read all these parameters from the actual stress strain curve for your steel. And this is the ultimate strength. So after peak, it is dropping little bit. Then this is the ultimate strain. Normally for steel, in case of earthquake loading, the ultimate strain is considered as 0.05. This is not the maximum strain. The monotonic stress strain curve, if you follow, the maximum strain of steel is it should be at least 14.5% as per Indian code, and similar range if you follow all other codes also. At least 12% if you go to any code, either European code or American code, everywhere it will be at least 12%. Okay. But in case of seismic loading, this is kept at 0.05% because of low cycle fatigue phenomenon. Okay. The same thing you'll define for the other direction. I'm just assuming the symmetric curve for both the directions. It need not be true, depending on if you have buckling probabilities, then the properties on the compression side will be different. Then this is pinching for cyclic degradation, and this is also cyclic degradation properties. These values you have to calibrate, these cyclic degradation properties. So now if you want to see under cyclic loading how this model behaves, you can click on any of the cycle protocol. Let's say I want to see this one, and here you define the maximum strain up to which you want to see. Okay. So if you use this material and apply lateral load in a cyclic loading protocol, so up to a strain of 5%, this will behave like this tail rebar material. Okay. So now let us go to the steel 02 model. This is the steel 02 model. We can define the similar properties here. 500 yield strength. Then this is 0.1. This is zero point 0.8. So what I am doing is, instead of having a smooth curve, I am just sharpening the edges here where the direction means stiffness changes. Okay. So then these are some other parameters. You can just explore this one. Now the problem with this model is it does not have any failure strain. Okay. So it will continue this same protocol, uh, means without any failure. You can load it up to a ultimate unlimited strain, but it will never fail. This is the problem here. Okay. And it does not have any cyclic degradation. Now if you see, again apply the same. Let's say I am defining a strain of 20%. Here you see how it is behaving. So it has a kinematic hardening, but no softening. It will never degrade. Okay. So that's why this model is not realistic for earthquake loading assessment. Okay. You need some material model which can degrade under cyclic loading. Okay. That's why you should not use this model without any cap. There is a option available like min max cap. You can use this, wrap it in a min max uh, section wrapper, material wrapper. There you define the maximum strain as, for example, 0.05. So what will happen once this material reach 0.05 strain, then it will indicate as failure. Okay, but again, there will be no cyclic degradation. So that's why you need a material which can appropriately simulate the cyclic degradation, and this can be done using the hysteretic material I have defined just before this. Okay, so I just wanted to show you the difference between these two materials. I hope it is clear now. Okay, so we are done with the definition of materials, and we have also defined this section. Now we have to define the elements. So now first we'll call the elastic beam column for beam elements. See, here you do not edit any properties because this interface is not optimized for specific material or specific element. You just define, call them, and from this left panel, you always edit any property you need. Okay, you just call each of this model from here, but do not edit anything here. So this is elastic beam column. Then we need a zero length for beam hinges. Then we need another elastic beam column for columns in case of the elastic model. Then we need beam width hinges for nonlinear model for columns. Actually, we'll use three different elements for columns in case of nonlinear model, just to demonstrate. There is nothing like we are comparing the result. So what we are doing is we have taken three material: force beam column, then displacement beam column, then beam width hinges. So these three will be used for nonlinear modeling of columns. Then elastic beam column will be used for the elastic model. So now the elements are all here. First, we'll start with the elastic beam for beam elastic. The dimension is 250 by 450. And update. So all the properties are updated. Now here you define the stiffness modifiers. Uh, but since this is elastic model and again it is just demonstrations, we will not be using any stiffness modifiers here. Okay. But if you go to code, according to Indian code, for beams stiffness modifier is 0.35 for the bending stiffness. Okay. So we are just leaving this as it is. Whenever you model your actual structure, you will use the stiffness modifiers defined in your code. Okay. Then click OK. Then zero length. Now see, there are 6 degrees of freedom, and this zero length is actually for defining the nonlinearity in your beam models. Okay. So here you define the materials for each of the degrees of freedom to simulate the nonlinearity in particular degrees of freedom. Okay. Now, in this demonstration, what we are going to do is we'll only simulate the nonlinearity in the flexural response. Okay. Then uh, other degrees of freedom will be provided with the elastic material. So that's why this elastic material, what we have created earlier, this one, first one, is for this purpose. So the ID is 1. So here you see everywhere 1. Okay. So by default, it is already calling this first material. Okay. Now this material is uh, appropriate for the UX, UY, UZ. And now let's say I am modeling the members along Y. So this is the direction for this beam. What will be the degree of freedom for the mx and my? Okay. So here you have two options. One is going by the local axis system, another one is going by the global axis system. So if you go by the local axis system, it is uniform for all the members. But if you go by the global axis system, it is different for x direction and y direction. Okay. So I'll show you with the global axis. Then after that, if you have any doubt in the local axis, we can discuss that later on. Okay. Now, in the global axis, what happens? Here you see this is your axis system, and our members are lying along the x direction. Okay. So your bending will be about y and about z. So in plane bending will be about y, and out of plane, sorry, torsional will be about z. Sorry, that is not torsion. Out of plane bending. Okay. So yz means this one, ry and rz. So you are defining this here. This one, the id is 2. beam hysteresis we have already defined. So that same ID we are calling here. Okay. So now the same thing you have to do for the other direction beams also. So what we'll do, let's say this is for beam hinges along X. So we can just copy this one, right click, add copy. Okay. So another one is copied here. You can double click this one to open. Then beam hinges Y. So now for Y direction means the members in this direction. Okay. So the bending in plane bending will be about X and out of bending will be about Z. So this is going to be 4 and 6 degree of freedom. Okay. This is 4 and this is 6. Fifth one will be again elastic and click OK. So this is done for beams. Then this is elastic beam for columns, and the dimension we have used was 450 by 450. Again update, and again when you want to define the stiffness modifiers you can do it here. Okay. Then this is beam width hinge for columns. This will be using for the nonlinear model. We are just making it ready at this stage. And this is the plastic hinge length you have to define. uh, Either you can use any expression if you have, or by thumb rule it is half of the section depth, so it is going to be 225. And here you define the fiber section. We have one fiber section defined, so in the drop down menu you can get it. If you have multiple one, then you have to select uh, out of them. And again this is the plastic hinge for the, sorry, fiber section for the other end. Then here you define the grade of concrete, and this is the coefficient for the Young modulus of concrete. Okay, so as per Indian code, it is 5,000 root FCK. So you might have some, if you are out of India, so you might have some other codes following according to that. You can define here. Update. Then okay, this is also column. Other element, displacement beam column. Displacement beam column. And here you define the number of integration points. Uh, to make it easy to run, let's say I'm defining 3. Okay. 2 sections at the ends and one intermediate section. And here again you define the fiber section. Then click OK. And this is the force beam column. So again, column, force beam column element, 450 by 450. And here you define the integration method. Let's say I'm going to use this one. And here you define the section, fiber section for end, as well as fiber section for intermediate region. Now here, as I told earlier, the elastic section is not yet implemented. We'll do it, and we'll share the updated version soon. So when elastic section is available, normally the interior region of either beam or column will be mostly elastic. So that elastic section you can assign here. But for now, that is not available. So only option is to use the inelastic section itself if you are using the force beam column. Otherwise, you can go with the uh, beam with hinges. There you by default interior is taken as elastic. Okay. So we have done everything with respect to material and element definition. Now we need to define some other properties like geometric transformation for beams as well as for columns. So we have defined two geometric transformation, one for beam, another one for column. Then we have to define time series for load applications. So we need to define gravity load for that one time series I'm defining. Then we need to define the pushover load for that one, and we need to define time history load for that another one. So total three time series we have defined. Similarly, we have to define three patterns. This is TCL pattern. You have to define one, then two, and three. Then we have to define mass. So we'll edit everything later on. I'm just defining everything what I need now. Then we need to define damping for nonlinear analysis, for not for linear analysis. Then we need to define the rigid diaphragm. So let's say this is rigid diaphragm. So we have defined everything as you can see here. Whatever you are defining here, everything will be stored here in this left panel. So here you'll be editing after calling the properties from this. And we can define different load types. Let's say I'm defining floor live load. Then let's say infill wall load. Then floor slab dead load. You can just give some name, whatever you feel comfortable. So these are not OpenSys commands. These are for easiness of modeling we have implemented so that you can separate each load types during application and later on when you want to investigate any particular, let's say, result with respect to this load, something like that. Okay. Now, so, okay, so this is geometric transformation for column. You have to define this vector appropriately. If you define this one in a wrong way, then your model will not run. Okay. So for columns, mostly this is the first one. Okay. That will be one or zero. So you keep first one as one, then remaining as zero. Now, if you want a detailed discussion on this, follow our previous tutorial. We have explained this in a very detailed manner. And also we have uh, like manual calculation of how to calculate those vectors. For example, this one uh, local z. Actually, this is what you have to define in the software. Okay, so how to calculate that vector that we have shown here for beams as well as for columns. Okay, so this is for beam. You can see 001, and this is for column. This is 100. Okay, so I'll share this calculation also with you, and you can also refer the previous tutorial how this calculation you have to follow that discussion we have done there. So this is for column and this is for beam. So this is 001. Then okay. Then this is the pattern you have to use for different load application, and each pattern should be associated with a particular time series. Now second pattern I am connecting with the time series 2, and the third pattern I'm connecting with the time series 3. Okay. And the second one is for the push overload application. So you can either keep it as linear, or you can call a load pattern, means a loading protocol from a text file or something like this, using this path option. Okay. Now when you are using this path there, this is the pushover loading protocol we have used in this demonstration. So it's like linearly varying from 0 to 1 in 1,000 steps. Okay. So total 1,000 steps, but the variation is linear. Okay. So you can define the number of steps. As the number of steps increases, your analysis runs slower. Okay. So this is what. And for pushover analysis, you need a uh, like higher number of steps. Okay. Then here you define the time step for each one, so that you can define, let's say, 10 seconds for each step. So total we have 1,000 steps multiplied by 10, so it is 10,000 seconds. If you convert this into hours, so it becomes 2.8 hours, roughly 3 hours you can say. So what it means is your building is loaded continuously for 3 hour duration using this load pattern. Okay. So it is like gradually, the load is applied gradually. This is what we do in the pushover analysis. But same thing, if you, let's say, you are finishing this one in 100 steps, means this is like sudden impact, fast application of load. So this is not the representation of pushover load analysis. Okay. So that's why you give some long duration load application when you run the pushover analysis. Then this is for the earthquake load application. Again, we have to call a earthquake time history file using this path option, then browse again. And here I have some three earthquake time history available. Let's say this is the Imperial Valley earthquake. Let me show you. So this is the Imperial Valley earthquake time history. The earthquake occurred in the year of 1979, and we have total 7,569 steps here, and the step size is 0.005. So if you want to calculate the total duration of this earthquake, this is 7,569 multiplied by 0.005. So the total duration is 37.8 seconds. Okay. So you can just open this, and now see, you click on this option, and here you see the time history and response spectrum of that earthquake is displayed here. Okay. You can just reformat this one in the way how the software accepts this one. Okay. So here it is asking header line to skip, how many lines you want it to skip. Let me show you once again this one. This is the earthquake file we are referring now. We have total 1, 2, 3, 4 lines which should be ignored when you are reading this data. Okay. So that's what you are assigning in the software. 4 lines on the top to be ignored. Then data points per row is 5. 1, 2, 3, 4, 5. So this you are defining here. Then time step we have seen, this is 0.005, and scale factor. Now see, the software is unitless, so you have to convert the unit of ground motion to the unit in which your model is built. Okay. So the unit of ground motion is in G. Okay. But your model unit is Newton mm second. So the conversion factor will be 9810. Okay. So if you are working on any other unit system, accordingly you will provide the scale factor here. Then damping ratio is 5%. If you want to, like, this response spectrum is displayed for 5% damping. If you want to see for other damping ratio, you can just type it. Okay. Then click on this curate and save. And accordingly, your file name and path is changed to the formatted file, and also the timestamp is updated here. Okay. Then click OK. So this is how you can define the ground motion time history in our software. And then you have already called this one. This is for earthquake time history. So you will follow this uniform excitation. Okay. And the time history file is third one already we have done. And here you mention the direction of earthquake load application. Okay. Now we are assuming that the loading will be applied along the x direction. So this is one. Then click OK. So this much is regarding the definition of all the required properties what you need for modeling your structure. Now we'll assign one by one. Okay. So first let us assign the properties for beams. So what you can do is, uh, you have two options. Either you can go to this one, then click each beam separately. Here you see, I have selected a beam here, and the member corresponding to this is highlighted here. Okay. So you can assign the properties for each beam separately here. Here you can select either frame modeling or fiber modeling or other modeling type. For beam, we are choosing the frame modeling, like elastic beam column element. Then accordingly, which element you want to assign to this member. So this is the beam elastic. This we are going to assign here. And if you are building the nonlinear model, you also enable the plastic hinges. Okay. So it will define some extra nodes required for connecting the plastic hinge to the elastic beam. Then you have to define the hinge for both ends. Okay. So we are assuming same properties for both. So for x direction beam, we have to select a particular hinge, let's say this one. Then here you define the transformation tag. We have already discussed this one. Second one is for the beam. So you'll select the second one here. Okay. Then click OK. So these properties will be assigned to this member. But we are not going to do in this way because it will take a lot of time. So what we'll do is we'll select all the beams, because for X and Y it is different. So we'll first select the beam for X direction, then we'll do the same thing for Y direction. Okay. So click on this option, sorry, this button. Then you drag your mouse here. You can select it this way. Suppose you are defining the same properties for all the beams. So there is another option. You can go to select and select beam. But if you click on this one, all the beams will be selected. But now I want only X direction beams to be selected. So that's why I have to do it this way. Then go to assign properties. Okay. And here it is frame based modeling, beam elastic. And now we are not defining the hinges because our model is elastic so far. So when we'll be doing the nonlinear modeling, that time we'll enable this one and assign the hinges here. Okay. For now it is just elastic. So click OK. Now if you turn on this one rendered view, you can see uh, beams for these directions are assigned. Okay. Now same thing you can do for the other direction. Just move it this way so that you can select the beams. Okay. Then again click on this button. Now you can drag your mouse and again go to assign properties. Okay. same same beam element and transformation tag 2. Click OK. So done for beams. Now the same thing will be done for columns. So for columns, since we have the same properties to be assigned to all the members, so instead of doing it this way, we can directly go to select and select columns. Okay. So all the columns are selected. Now you go to assign and assign properties. Click OK. Then for this elastic model, we are assigning the uh, column elastic, this one elastic beam column element, same element, but the transformation tag now will be one. First one we have developed for the means we have defined for the beams. Okay, then click OK. So now you can see all the beams and columns, materials, elements have been assigned, and now we can assign the support conditions. Select, drag your mouse and select all the base nodes and go to assign restraint fixed. Click OK. So now you can see the support conditions are assigned here. Then what else we need to assign? We have assigned the elements, we have assigned the support conditions. Then we can go to the load applications. Okay, so we have defined three kinds of loads. One is the infill load for the walls, another one is the live load for floors, another one is the dead load for floor slabs. Okay, so first let us define the means assign the uh, infill wall load on all the beams. Just for simplicity, what we'll do, we'll select all the beams and apply the uniform load throughout. But in real, you will not do that. You'll select the specific members and apply the load appropriately. Okay. So what we will do, just to save our times, select all the beams, go to assign load, and here you select the infill wall load and the pattern. Okay, we have defined three patterns. First one was for the gravity load application, then second one was for the pushover load application, and the third one was for the earthquake load application. So we'll select the first one, and here you will select, because we are going to define the member loads uniform load distribution. So you select this one, element trapezoidal load, and just because this is the first application, it doesn't matter. But if you have like multiple load application, there you define, means select these options appropriately. Okay, now it doesn't matter, and the direction will be global minus z. Okay, so now let's say I have a wall thickness of 250 mm. So 0.25 into the density of bricks, for example 20 MPa, into the height of wall. So below beam, approximately let's say 450 is the height of beam, means depth of beam section. So your wall height will be 2.6 if you have a floor height of 3 meter. So it gives you a uniform load of 13 Newton per mm. So element trapezoidal load. See, in OpenSys, you do not have a proper trapezoidal load, because this has been written keeping in mind the future upgrades. So that's why we have developed it this way, so that in future when trapezoidal load model will be available, you can use the same model. So far it is not available. So you just take this and apply the same load intensity for both the ends. Okay. So it will give you a uniform load distribution. So it is showing you assigned to 0 nodes and 580 elements. Do you want to display the loads now? So the loads are applied. If you want to see it properly, just select a particular plan view and see it this way. So here you see the loads are applied. Okay. You can disable this one going into this and hide loads. Now, this is one type of load we have applied. In the same way, you have to define the other types of load. So there are grids displayed in the background. Actually, we have not yet optimized this one. So what we'll do is save this model and open once again. After that, it will be gone. Okay, so go to a plan view. Now we are going to assign the flow live loads. Okay, so let us assume a live load intensity of 3 kilonewton per meter square. Okay, so our unit is Newton mm, so it will be like 0.003 Newton per mm square. Okay, so you select a particular plan view, then go to this select and enclosed area. Okay, now select the flow panels, then go to the next floor, do the same thing. Now I'll not apply for all the floors. I'm just showing you how to do that. Okay. In a similar manner, you can do it for all the floors. Then go to assign loads. Now this is floor live load, and again the same pattern. And now you have to select this one area load. And here again, since this is the first time you are applying, it doesn't matter. Okay. And intensity now is 0.003, and the direction is global minus z. Okay, and here you can see selected panels 48. So I have selected for two floors, so total 48 panels are selected. Click OK. Yes, and now again you can see actually it is showing only for one floor, but it is not like that. The load has been applied to all the floors, means two floors. Okay, now you can turn on a particular plan and see. So this is your load application using the area load concept. Now, how OpenSys does it is in OpenSys you do not have a area load concept, okay, or you do not have a, triangular or a trapezoidal load concept. OpenSys has either point load. You can apply a load at a particular point in your member, or you have a uniformly distributed load. Okay, so what we have done is we have used the concept of point loads and applied in such a manner that uh, all the point loads together represent either a triangular shape or a trapezoidal shape or any shape which you expect from your area loads. Okay, so if you read the TCL script for this load application, you will see a series of point loads applied for a particular members. Okay, and if you add all those point loads together, there you'll see it is equivalent to the load intensity of this pattern. Okay, or any other pattern applied to a particular member. Okay, so I just wanted to let you know what is the concept behind this one, because if you go to the OpenSys, you will not find this concept there. So you disable this one, then similarly you can define the dead load for the floors. So let's say I want to define for a particular floor. Again, go to select and close the area. So I'm doing just for one floor. The same thing you can do for all the floors. Go to assign, then assign load. Now it is floor slab dead load, and the pattern is same. Again, area load. And so now let us assume a thickness of 150 mm for the floor slabs 0.15, and the unit weight of concrete is 25. So it comes out to be 3.75 kilonewton per meter square. So again, if you convert this into Newton mm second unit system, it is 0.0038 approximately. Okay. Then direction is global Z again, and click OK. So again, this is how it is applied now. So these are the shortcuts you can use in the software to fast track your modeling of your structure. So now we are done with the load application, although I have not applied for all the floors, but the concept is shown. You can use the same thing for all the for whole structure. Here one additional floor is coming. Let us disable this one. Go to edit stories and reduce it. Okay, let's save it. So now we are done with the load application for the gravity loads. So what we can do is, yeah, one thing is left out, the assigning of rigid diaphragms. So for that, we'll increase the size of nodes because we need to pick the nodes for that. So we start with the first floor. What you do is, first pick your master node. Let's say this is our master node. Then pick all your slave nodes. You just drag your mouse there and click on whichever story you want to, means you are referring now. This is first story, and click on this. So the rigid diaphragm is assigned to this floor. Then go to the next floor and again pick this one and pick slave nodes, and this is next story. Then go to the next floor, click on this, same thing, just repeating the same thing. So give me 2 minutes, let me finish this one. Hello sir. एक webinars, webinar, webinar ऑनलाइन, नहीं अभी टाइम लगेगा, टाइम लगेगा. Okay, so we are done with the rigid diaphragm. So this is how you can see rigid diaphragm assigned to your structure. Now we are left out with the application of pushover load and the uh, earthquake time history load. Earthquake time history load we have already assigned, and pushover also we have not assigned. Okay, so let's first analyze the structure for the modal analysis and the linear time history analysis. Then we'll go to the pushover analysis. Okay, so this is done. Now you can go to the modal analysis. Here you define number of modes. Let's say I want we need three modes to represent each story. So we have total 10 stories. At least 30 modes we can define here, but let's say I want to define 21. Okay, and here you call your OpenSys, and you select a folder for storing the TCL files. Okay, TCL model. Okay, there is something wrong. Okay, we have not defined the seismic mass. So this is according to your model unit system. Let's say for live load, we are considering 50% contribution. So most of the codes, I think, use 50%. Uh, then for infill wall, 100%, and slab dead load, 100%. Okay. And you also include the self weight of your members. Okay. So the self weight of beams and columns will be automatically calculated by the software. Then click OK. Now again run the analysis. Okay. So now it is correct. So your first mode period is 1.466. Actually, this is not the actual period because we have not applied all the loads. Okay. So when you apply the loads on the entire structure, this first period will be for this model 1.9 seconds or close to that one. Then the second period will be 1.8 or 1.7, something like that. I have already analyzed this for this structure earlier. There it was coming in that range. Okay. So after that, you can go to display result and see modal analysis. Here you see these are the periods, then frequency, then angular frequencies, and also the mode participation factor for each direction. Let's say this is the first mode. You have the period, then mass participation along X, then mass participation along Y. So the first mode is basically in the Y direction. Okay. Then second mode is in X direction. Then third mode is torsion. Then again fourth mode it is coming in Y. Fifth mode is coming in X, and sixth mode again torsion. And if you are targeting in case of earthquake means seismic design, we target at least 90% mass contribution in each direction. Okay, so that 90% for X direction is coming here in the eighth mode. Okay, then for Y direction it is coming in the seventh mode. Okay, So seventh mode, in the sense, this is the third translational mode for y direction, and eighth mode is the third translational mode for x direction. Okay, so this is what you can read from this one. Now, if you want to visualize the mode shapes, you go to this one, result visualization, and click on this one. And this is first mode, and increase this scale factor so that you can properly visualize this. So this is your first mode. Then this is second mode. If you want to increase the speed, so reduce this number, so you can control the speed also. Then this is your torsional mode. Then again, this is second translational mode for y. Then for x, then again torsion, and you can see this way. Okay, so this is about the modal analysis. So now we'll do a linear time history analysis on the same model. We already have defined the time history, and the damping we have not defined, I think. So let's define the damping. Our first period was around 1.4 second. Let me verify it once again. This is the first mode. We are running in the x direction. So the first mode period is 1.437. So 1.44 second, let's say. And we need a period corresponding to 90% contribution. So which is coming here. Okay. This is for x direction. So it is 0.27. So if you know the concept of Rayleigh damping, you'll understand we need to define two time period corresponding to a constant damping ratio. Okay. So the first period is 1.44, second period is 0.27. Okay, and we are assuming a damping ratio of 0.003%, sorry, 0.03 or 3%. Okay, for these two periods, and the damping for other periods will be calculated using the concept of Rayleigh damping. Okay, so damping we have defined. Then now we have to first define the recorders. What are the parameters you want to record? I want to record the nodal displacement. Click OK. I want to also record the nodal reactions. Nodal reactions. Then here you need to choose the reaction, and here you need to also choose at which degrees of freedom you want. I want three translational degree. Rotational response I am not recording now. Okay, and also if you want element response, so what response you want, global force, section force, or anything, whatever you want. Let's say we are not recording all this, and we do not have any fiber section defined here, so it doesn't matter if you click this or not. So disable this one, let's say. And what else we can define? Everything I think in place. So let's now define the analysis step. So first, this is the first step, gravity analysis. It will be static, and we can select the transformation or any other constant handler you want. So transformation is better actually. Then it is load control. We have load control option both for gravity as well as pushover. Although in pushover we do not prefer the load control. Okay. So the load will be applied in 10 steps. Okay, so that's why number of steps 10 and interval is 0.1. Okay, and here again you can select this number, and by default this is, actually I prefer this one. And here the tolerance you can define displacement based tolerance or force based tolerance. For linear analysis it doesn't matter, displacement based tolerance works, but in nonlinear analysis there is a problem. I'll show you what is the problem. But let's say now I am going for a displacement based tolerance, and again this tolerance will depend on your unit system. Okay, the maximum displacement you expect, and what fraction you want to use as a tolerance. Okay, so 100 iterations we can go for, and if you want to print anything in the analysis log, then you can click on this one. If you do not want to print, you can ignore this. Okay, then let's say I'm defining this earthquake load. Now we have to shift to the transient mode, and again transformation. Now let's say I'm using this HST, and the duration of earthquake was 37.5 seconds. It is 7569 into 0.005, so it is 37.8. So 37.8, and the time step of the ground motion was 0.005. Now here you see either you can use the 0.005 or any step size lower than that, but should not use any step which is higher than the step of your ground motion. Okay, and in that, since this is elastic, so it doesn't matter. In nonlinear analysis I'll show you what test type is most suitable here. Okay, now I'll use the same step size, means test type normal displacement based increment, and click OK. Now go to run and select a folder for storing the TCL. So TCL, this is linear time history. So the analysis is running now. It will take little time. Okay, so let's about this one, because we just want to demonstrate the workflow. We have performed the analysis partially, and you can visit the results here, story response plot, and here you see the response of drift ratio. Okay, so for whatever duration we have run the analysis, it has reached to a drift ratio of a little more than 0.4%. Okay, and you can also see the displacement little more than 60 mm. Okay, so if you want to see the animation, you can turn on this one and increase the speed little bit, and now see it is running. Or if you want to see it this way, you can also see it this, like this. Okay, so this is how you can explore the result here. Now you can also see the base shear versus roof displacement, although this was implemented for pushover, but it also displays the uh, result for the time history analysis. Now what you have to do, you have to see the control node for the roof. Give me a minute. So this is the node number 368. Okay, the control node we have used for rigid diaphragm definition. The same node will use for controlling the roof displacement. Okay, so you can go to display result, then this one, and select here the control node 368, and the direction of load application was X, then plot. So here you see this is giving you the base shear versus the roof displacement for the time history analysis. Although we have never checked this for the time history analysis because the implementation was purely for the pushover. So we'll go back to this uh, code again and see if it is appropriately giving the result for the time history analysis also. Okay. So you can also see nodal displacement here, and if you want to download this as the Excel file, you can go to this one and export as Excel file. Okay. Now, why it is important is if you go to the scripts, what has been stored here, for example, this one, this is your nodal displacement file. If you open this one, it is very difficult to read. Okay. So you do not understand anything. So that's why in the software you download it as a formatted file, and for which node, for which direction, everything is written here. Okay, so it's very easy to read. Now after that, if you want to export this for any other post processing, you can do it very easy way from the software. Same thing you can do for the nodal reaction. Go here and export as the CSV file. Okay, and also you go to result visualization and click on time history and the displacement where you have applied, and you can run this animation. So it is running very slowly. So actually we have just initiated, after that we have stopped analysis, so it is running only for 6.5 seconds here. Okay, so this is how you can explore the results. And when you have the fiber elements also, there you can investigate the fiber results also, that will show you in the nonlinear model. Okay, so this is about the linear time history analysis. And one more thing I think I forgot to show you, this nodal displacement versus reaction. Now say if you are interested in post processing of load displacement for a particular node, so you can select a node here, let's say the same 368, and the displacement of that particular node for the loading direction. So you can see it this way. Okay. So this is the nodal displacement only for that node. So these are the things you can do when you record the element forces and fiber sections, then these two options will also be enabled. Okay. Now, since we do not have any response parameters, so these two options are hidden. So that's all for the linear time history analysis. Then now we save this model and copy it for the nonlinear model. I think instead it will be better uh, since we already have this model ready here. The same model, all the modeling scheme we have shown. Okay, no problem. I'll show it once again so that it gets more clarity to you. Say nonlinear pushover. So now what we'll do is we have to introduce the hinges on beams, and then again either we can introduce the hinges on the elastic beam column in columns, or we replace them with the fiber based modeling. So we'll prefer the fiber-based modeling for beams, sorry, columns, and the elastic beam column assigned with the hinges on ends for beams. Okay. So first we'll replace the element for columns. For that, you go to select columns, then assign properties, go to assign, then click on the fiber-based modeling. First, we'll start with the displacement beam column, then similar way you can just replace them with the other element type and click OK. Now here you see we have two more options. If you want to simulate the bond slip for strain penetration region, you can use this. Then if you want to introduce shear behavior in your members, then you can use this one. So we are not using this now. So whenever you'll be using, if you have any doubt, or we'll conduct another session purely on this so that it gets clear to you. You can refer literature. There are a lot of literature available on this, how to simulate these element properties, and assigning is very easy. Just turn on this one and select particular material. Okay, click OK. Now columns are assigned with the displacement beam column element, and this is the fiber section we have used in that. And now select beams. All the beams are selected. Go to assign, then property. Okay, turn on this one, and now here you select the hinges. Okay, so now again we have to go by x direction and y direction because we have chosen based on the global axis system. So this is for x. Assign properties, extra node, and beam hinges for x direction. Click OK. Same thing you do for the y direction. So it is better if you decide the hinges mean zero length using the local axis system. Okay, so that is also possible. I have already shown. It's your choice. Actually, I prefer going by the global axis system. That's why I have done that. Okay, so it is done. Now, if you want to verify whether the hinges are assigned actually, what you can do is increase the size of your nodes, then select on any node and double click. Okay, so after that, this panel comes out. Here you see this is a corner node connected to three members. So out of them, one is column, so there will be no zero length hinge. Two beams, so you have two hinges assigned here. Okay, direction is also shown. One is in the east direction, another one is in the south direction. Okay, now let's say you select an intermediate node, for example this one. Double click. Now you see This node is connected to total six members, out of them two column members, another four beam members. So here you see one beam hinge. This is in west direction. This is in east direction. This is south. This is north. So using this direction, you can identify which hinge is in which member. Okay. So when you want to like delete any particular hinge, what you can do is you can identify easily and select that and press this delete button. Okay. In that way, you can also delete the hinges. For example, you have first modeled a nonlinear model. After that, you want to convert it into a linear model. Okay. So what you'll do, you will delete all the hinges. So either you can use this tab and select the hinges manually and delete, or else what you can do is go to select all the ghost nodes. Ghost node means it is representing the hinge nodes. Okay. Now all the hinge nodes are selected. You now just press to this delete button. Okay. So when you do this one, all the hinge nodes will be deleted. So after that, your model will be converted to the elastic model or the linear model. Okay. So these are the shortcuts you can use in the software. Now our nonlinear model is ready. So what we can do is we can perform the time history analysis again for this model. Okay. So so this is the time history and it's done. So we can run the nonlinear time history analysis. Okay, sorry, we were actually trying to run the pushover analysis. So what you have to do is you have to create a pushover load case. Okay. So what you do, first you select a node on top. Let's say I select this node. Okay. Then go to assign load. Then this one, you select this one, nodal displacement. And here you select the pattern. Okay. Second pattern we have decided for the pushover load case. Then you click on this one. You want to define the push overload based on the mode shapes. Okay. Now, since the model analysis is not performed, what we'll do is first we'll perform the model analysis again. Now, see, if you see the period, it is increased almost to twice from the previous results we have seen. That was for linear model. Pushover and sorry, model analysis is performed on the linear model, but now since our model is turned into a nonlinear model, so the period has increased. Okay. Although the mode shapes will not be different, it will be the same shape. If you want to verify this one, you can just go to this mode shape and play animation. Okay. So this is your, so now first mode is coming in the x direction. Okay. And the second mode is in y direction. So we need the mode shape. So what we'll do, we use this mode shape and apply the pushover load case for this one. So model, and now we have to run the analysis in x direction. So we have seen the first mode is in the x direction now. So you select the first mode here, and roof control node, it is automatically taking from the model. So here you see rigid diaphragm detected, control node at flow levels are taken from the diaphragm master nodes. Okay. So now if you want to assign any other node as the control node, you can do it here. Okay. But uh, whatever node you have decided for the rigid diaphragm, it is better to take this as the control node. And now here you select the roof displacement, how much you want. Okay. Now let's say I want to push my structure for a displacement of up to 1500 roof displacement. Click OK, and here you define the direction of application. Okay, we have defined the mode shape first one, and we want it to run along the x direction. So this is what we are doing now. Okay, and you do not have to do anything here, we have done inside that. Okay, click OK. So load assigned to 10 nodes, display the load now. Yes, here you see now the pushover loads are applied to your structure, and here you see all the nodes along each floor, and the degree of freedom means along the x direction. And we have defined the roof level displacement, and displacement for all the other floors were calculated by the software using the mode shape you have decided. Okay, so this is how you define the pushover load case in the software. Now you can go to analyze, define a step for the pushover analysis. We want to keep it as a static analysis and transformation, and displacement based analysis. Here you select the load path, then maximum increment per step. We have defined total 10,000 step, and maximum, let's say we want 1 second per step. And this is this one. And now if you go for the displacement based tolerance, your force imbalance will not be satisfied always. Okay, so it is better to go by the force based tolerance so that it also satisfies the displacement based tolerance. Okay, so now here what you have to do is, again this is unit based. Now how do you decide what tolerance you have to decide for forces? So roughly you can take the seismic weight or the base shear of your structure from the linear analysis, then assign 1% or 2% of that as the uh, tolerance for this analysis. Okay, so for this model, my seismic weight was around 70,000 kilonewton. So what I am doing is I am considering 1% of that, so it will be around 700 kilonewton. Okay, so instead of 700, I am assigning 1000. Sorry, not 1%. If it is 70,000 kilonewton, that divided by a factor of 10 to the power 5, let's say. So it is your seismic weight or base shear divided by a factor of 10 to the power 5 or 10 to the power 6. So that is how you calculate this roughly. Okay, so it is coming around 700. I am assigning a value of 1000. Okay, this is actually little bit tight, this tolerance. If suppose your model is not satisfying this, so what you should do, you have to relax this a bit. Okay, so you increase this number. So this is how you decide this parameter. Okay, but when relaxing, it should not be too high that your model like diverges and gives you incorrect result. It should not be that way. And I do not want to see any output. Means if you have any warning or something else you want to see, you can click on this option. But I do not want that. Just to clean the analysis log. Okay, then click this. Now what I'll do is I'll run the static analysis, then means gravity analysis followed by the pushover analysis. So this I'll disable. I do not want to run the time history analysis now. click OK. And now you can go to again analysis, then define recorders and see. I want to also record the fiber section results. Click OK and run. Now TCL pushover. So first step was the gravity analysis. Now pushover analysis started. What we can do is we can reduce the number of steps so that analysis runs a little bit faster. So for that, what we can do, go to this time series and reduce this, make it one. So we had total 1,000 steps in the loading protocol. So 1,000 into one, so it is total 1,000 seconds now. Okay. So now you have to modify this. Okay, we do not need, because if you go by the other option, instead of static, if you go by the transient option, that time you have to modify here also. For this, we do not need. We can directly run it. So let's wait for 2 to 3 minutes, because I have to show you the pushover curve also. So the analysis is over. Now it will take little time to save all the results. Now you can go to display results and the pushover curve. Here you again select the control node for the roof and the direction of load application, then plot. Now here you see this is the pushover curve. Here the problem here is that it is we have applied a displacement of up to 1500 mm. In terms of drift ratio, it is 5%. So in 5% drift ratio, we expect softening or degradation. But here it is like increasing. If you apply the load further, it will still increase. But here at 200 mm displacement, the yielding has already occurred. So from 200 to 1500, it is showing a ductility of roughly 7.5. Okay, which is not we expect in general. This problem has occurred because of this one. We have not considered the p delta option. Okay, so what you can do is you can select the p delta and run the analysis once again. After that, you'll see it will degrade after some displacement. Okay, which is the real behavior. Now, in this example, we have not considered that P delta analysis. That's why it is showing continuously increasing, although it has yielded very at like very small displacement. Okay, so I am not going to run it once again. You can check it yourself once running with P delta, another one without P delta, and compare the results. Okay, so this is about the pushover analysis. Now, if you want to see the deformed shape of this one in animation, okay, so you can do it. So this is how it is deforming under the pushover load application. If you also want to investigate the fiber results, okay, so for this element type it is not working. Actually it was implemented for the force beam column and the beam with hinge element. So since we have assigned the displacement beam column element, now it is not working for this element. So we'll look into this and update accordingly. Okay, so I'll show you using the other element. Now before that, let me show you the time history analysis as well. So there is nothing different now. Just you have to run time history analysis. We have already seen how to perform the linear time history analysis. Now our model is nonlinear, and the same thing we have to run once again. आता हूँ, time लगेगा आप लोग को. So now it is performing the nonlinear time history analysis. So let's not wait once again for this one. I already have this model analyzed. Let me open that and show you some results there. So this is again which element? I think displacement beam column, you cannot see the fiber result. So what I'll do is I'll select the columns and replace them using the beam with hinge element. Then you can go to the result visualization. See, what we are displaying now is the fiber stresses. Okay, or you can display the fiber strain. So accordingly, your fibers are updated here, and you can click on any particular fiber and it will show you this plot. You can see either time versus stress or stress strain curve itself. Okay, so we have just initiated the analysis and aborted that. That's why the initial stage it will be linear elastic behavior. Okay, so now here you can also read what fiber, either it is steel fiber or concrete fiber. Here you can see the description. This is cover concrete and the ID, it is zero, named as zero fiber. And you can select steel fibers also. This is one of the steel, I guess. This is another steel. So it is named as rebar 11. And again, you can see this stress strain, how it behaves. Okay. So this is how you can investigate the fiber sections for each individual fibers during a particular analysis to see how it has actually behaved. Okay. So you can identify any failure occurred in any fiber, and appropriately you can conclude your assessment. Okay, so this is regarding the three kind of analysis. And now lastly, what I'll do, I'll show you by running the same scripts using the um, command prompt based analysis. Okay, so these are the TCL scripts generated by the software, and if you could see, this is for the pushover analysis. Okay, so what I'll do, I'll open my terminal, then type OpenSys. So now it is in OpenSys. So type source source. The source is this one main file. Okay, so if you go inside this file, it is calling all the necessary files. Okay, so I'll run this main file, main.tcl, and hit enter. So the same pushover analysis what you have performed in the software is running in the command prompt now. So this is the traditional way of performing the analysis in pushover. If you do not use any software, GUI software like the one you have seen here, REOS. So what you do, first you prepare your model using these scripts, then you run from your command prompt. Or if you are using the OpenSys Spy, then you can use any Python interpreter. There you run your analysis. Okay, so this is the other way. So this is very handy. Even if you want to write create your model, then if you want to use the same model for running in, for example, HPC, okay, supercomputers. So there you can use these scripts, and accordingly, if you want to update any parameters, you can just open any of the scripts. For example, element. So these are the elements applied to your model. So if you want to update any specific element or any other properties in your model, you can update it and run from anywhere you want. Okay. So I'll close it now. And this is all I wanted to discuss in this session. Now, I think the things are very much clear about the software, how our software works. And now I would like to know if you have any questions. Okay.
Hello, sir.
Please, yeah, please.
I want to ask, can we model a soil domain in this software?
Yeah, you can model, but let me show you. If you go to assign configure soil domain, so it shows you that SSI model is available in professional edition. Now the thing is that model is still under development, and we are testing this one right now, and it will take another few months. So uh, we are expecting this to be released in the month of March 2026. Okay, or maybe before that also, depending on how much it takes time to get validated. Okay, then similarly we have another model. Let me show you this one also. If you are working on seismic risk assessment, let's say incremental dynamic analysis or multiple stripe analysis for probabilistic risk assessment, there we have another module, this one. Okay, so what it does is, instead of running analysis for a single ground motion, you define a number of ground motions, let's say 20, 30, something like that. It will run all the analysis together, parallel, using the parallel processing. Okay, then also it gives you the idea curve. If you are running incremental dynamic analysis, it will gives you the facility curve, it will gives you the final calculated risk. Same thing when you are running using the multiple stripe analysis. Okay, so this is another module available. So whoever is interested, this module is already validated, so it is available on request. Okay, but the version now we have demonstrated here, it is not available. This will be available when you request for the same. Okay. Yeah. Any other question?
Sir, we can run both non-linearity in soil and material at the same time in this.
Yeah, yeah. You can do whatever time is analysis I have performed now. The same thing you can do when you assign the soil domain below your structure.
Okay, okay, sir. As far as foundation concern, we can assign it as a spring and dashboard.
You can assign as a Spring dashboard. You can assign as a contact interface where you define your foundation, then interaction between the soil and foundation, and soil will be modeled using the solid elements.
Okay, okay, sir. Thank you.
Any other question from other people?
Sir,
Okay, fine. Yeah,
is this video available later on YouTube?
yeah. I'll share through email. You can
Oh,
you'll get the link, so you can download the recorded video.
okay, sir. Thank you.
Okay. So if there is no other question, let's close this session, and hopefully we'll meet again with another session. And thank you all for your participation.
Thank you, sir.